Hello, I'm going to talk about a programming language, Elisa, that I'm currently making. A question many people often ask is, do we really need another systems programming language? And the answer is obviously we do not. But it doesn't hurt to have some new ideas. So Elisa has 3 basic principles, and that is reject all obviously slow programs, and then you take that subset of programs, and then you reject all obviously unsafe programs, and then you make writing those sort of the default path and making it as pleasant and appealing as possible to write those programs. So what sets Elisa apart from other systems programming languages are several things, but I'm going to first talk about the memory management. Elisa does use a region-based memory management model. And the way it works is the compiler performs a lifetime analysis of all heap allocated objects. And this is similar to the way Rust does things. The difference is that Rust uses RAII pattern, and this does make sense for certain types of things, but I don't think it's a good, necessarily a good fit as a general purpose model. So in Elisa, it uses a system where you have these parallel stacks, and these arenas, they you use the lifetime analysis to figure out all the lifetimes of the objects, and then the objects are pushed onto the arena that has the same lifetimes. So when the static the compiler does perform lifetime analysis and then figures out which objects need to be heap allocated, and then it determines the lifetime of these objects and which arena it's going to be allocated to. So instead of you using new and delete or smart pointers and stuff like that, this can often lead to heap fragmentation and a lot of individual repeated allocations. So Elisa creates a number of stack-like arenas for heap allocated objects. So instead of just having one regular stack, you basically have several stacks, but for heap allocated objects. How many of these stacks you need depend on the amount of lifetimes that the program finds. So at compile time, the compiler figures out how many of these arenas are necessary, and then the runtime just reuse these. So when one lifetime is reset, it is then reused for the next lifetime. When an object is allocated, it is pushed onto the arena that corresponds to its lifetime. Other objects with the same lifetime are pushed onto the same arena. When that lifetime ends, instead of freeing each object individually, Elisa just simply resets the stack pointer. The memory is not immediately released back to the operating system, so instead it is reused for the next suitable lifetime. And all of this is already figured out at compile time. So it doesn't do anything like Go, for instance, where it has a runtime that at runtime tries to do memory decisions. It's all ahead of time. There's some overhead from this strategy, and that is that when an arena grows, it needs to allocate more space. Dynamic arrays or other collections, they get their own arena or own stack. So if a dictionary or if you have a dictionary and a dynamic array that have both the same lifetime, their stack pointers are reset at the same time. And that is the time where they are no longer needed. And then those stacks are reused for the next lifetime. This means that you can freely push elements into that collection at all times. It is encouraged that you resize the array first and then you fill it, rather than using the push function to just repeatedly push, because then it needs to figure out if there's enough space in that stack before it with each iteration. You can optimize this away, but once you rely on compiler optimizations too much, you lose the predictability of performance. You no longer need know how the compiler is going to respond. So there's a trade-off. Do you want your compiler to optimize away anti-patterns, or do you want to get predictable results? So there's a trade-off between ergonomics and predictable performance. Generally, the Elisa compiler can figure out most, if not all, lifetimes at compile time. But potentially there could be some lifetimes where you need to specify the region manually. You can also create your own regions and specify the lifetimes if you need to. I'm going to clear up what I think is a misunderstanding around garbage collection. And why I don't think that Elisa or Rust or any other language actually gives you garbage collection for free. What a garbage collector gives you is not just the convenience, but it also gives you that guarantee that no matter how strange or nonsensical your program is, memory will still be managed correctly and safely by the runtime. So when people say things like automatic reference counting or RAII gives you garbage collection for free, I think that's somewhat misleading. The garbage collector gives you a guarantee that memory management is handled for you by the runtime in a sensible way. So for instance, when you have automatic reference counting, you need to break cycles and use weak references, and then you lose that guarantee the runtime doing things for you. So the value of garbage collection is not really that you have to think about memory management, but is that you get the guarantee that memory management is handled for you in a sensible way. One of the downsides of region-based memory management is that certain programs have unusual or difficult lifetimes. So, for instance, graphs, trees, or other structures with complex ownership, they can create cross dependencies that make resetting the stack pointer unsafe. So unless you use certain language tools that Elisa has, those programs won't compile. Another issue is that when you're dealing with very large objects, let's say you have a dynamic array with 1 billion elements, or you're working with the extremely large files or data sets, arenas are lazy in their deallocation, and they reuse the memory instead of immediately freeing it. That means arenas are not always the right tool for, let's say, very large data or programs that need more ergonomic use of memory. So they basically have a tendency to consume more memory. But memory is still quite cheap. So it makes sense to optimize for execution speed rather than memory usage. So in the cases where you are going to deal with very large data, you will need something like a custom allocator or a different allocator strategy. And this is where things like linear types that Elisa supports, or RAII style research management makes sense. Another thing is Elisa focuses heavily on correctness and particularly verifiable programs. So as AI becomes more common when writing code, we need better tools to ensure that programs are not only correct, but that their behavior and correctness can be verified. So it's impossible to ensure that your program is bulletproof, but we can get a lot closer to this ideal by investing into stricter semantic checking rules and type systems. So this means that Elisa has incorporated features such as refinement types, type states, guarantees that loops and functions terminate, and generally stronger compile time constraints. So the goal is to catch all obvious mistakes at compile time. So the compiler acts sort of like a static checker linter, as well as a navigation system that guides the programmer towards healthier programs. Not only does the Elisa language focus on correctness, but it also focuses on having the compiler ban certain anti-patterns that lead to poor performance. So this makes it harder for beginners and experts alike to accidentally write very slow programs. This doesn't guarantee that every program will be efficient, but it makes obviously inefficient patterns harder to write. Over time, features like time complexity tracking can make it even harder to introduce slow behavior by accident. So correctness is all about making mistakes harder to make. And By design, the language should make it difficult to do something unintentionally. That is sort of the guiding philosophy behind Elisa. Thank you for watching.